Okay, so welcome back to the lesson. What happens today is as follows. Firstly, we would be going through some of the topics in the lecture notes set number 3. We will probably be talking about the wave motion at the beginning, and we should hopefully cover the oscillatory motion as well, which are chapters 15 and 16 in the textbook. And later today, I would be explaining the situation of the midterm 1. Although I would not be going through the solutions because the solution is actually posted on Learner Poly already, I would leave it to you to read through the solutions. And the marking has to be explained a little bit. The marks are already out, but if you check it now, there are some changes. So I might spend just 1 or 2 minutes to explain the situation at the end of the lesson. Okay, now at here, we have already moved on to the lecture set number 3. So as you attend the last lesson, you have the idea what this set of notes is about. It is mainly concerned with another major topic in the mechanics, which is concerned with the waves. So it is actually in between the mechanics and the wave properties. It is actually a big topic of its own when you move to physics 2 later in the semester 2. But many of the concepts, they are related. Many of the concepts, they are related. They are related to the mechanics. And we will be talking about it in the oscillatory motion. So it would be something related to what we call a simple harmonic motion, as we'll see later. At the beginning of the lecture notes number 3, we talk about the descriptions of the waves. There are various ways in which we categorize the waves according to how they travel, according to the medium of the transmission, and according to the direction of particle oscillation. So at here, we would be looking at the traveling waves. We will be looking at the traveling waves, which involve the energy of the wave traveling from the source to the surrounding. And later in lecture notes, we would be talking about stationary wave, which by itself, the name is quite misleading because the wave energy is actually not stationary, not standing, but it involves also traveling waves, which are interacting with one another. So that is the topic of the superposition of the waves and interference of the waves. But that is how we call it. And we have also categorized the waves according to the medium of transmission. So we have the mechanical waves or the material waves. Some kind of a energy or wave transmission would take place in a material medium. For example, it can be air, it can be water, or it can be solids. It requires the disturbance of the particles in the medium to transmit that energy. On the other hand, you have the electromagnetic wave, where there is no disturbance of the particles, or even the wave can be transmitted in the absence of the material medium. It just relies on the disturbance of the electric field and the magnetic field in the space. So light, for example, visible light from the sun to the earth is transmitted through such a disturbance. It can take place in vacuum, so no material medium is required. And generally, the waves involve the particle motion as well as the transmission of the energy. And with that, it comes to a point that is sometimes quite confusing to the students. You have in the wave energy that is transferred over a distance. So you will see, for example, the wave that is setting the oscillation of the particles over a distance. So sometime later, you will see that, okay, sometime later, you will see that the particles would be distributed like that due to the movement of the wave energy. So the blue curve at the time t2 and the red curve at the time t1. T1 is later than t2. Of course, for that to occur, you could see that the peak position of the wave would be traveling. So that refers to the speed of the wave, which if you go a few pages later, it can be obtained by the equation c equals to f times lambda. So that is not much of a problem so far. But later, you will see that there is another speed or velocity that is involved in the motion, and that is the velocity of the particles in the medium. Consider a particular particle in a medium. Say we just focus on the red curve. We focus on the red curve. The particles are not stationary. As we know, in the wave, the material medium contains the elements, and they could be disturbed, but they would be disturbed from the equilibrium position. Here is the equilibrium position. Sometimes they would move up, sometimes they move down. So there is a velocity associated with the particle itself during the wave transmission. This is different from the wave speed c. The particle speed c, let us call it u, for example. It is the speed of the particles in the medium. Whereas c is the speed in which energy transmits. Is the speed of energy transmission. Sorry. They are two different things. The particles, they could be, for example, in a string, they could be oscillating up and down. So sometimes they are traveling with the positive velocity in the y direction, sometimes with a negative velocity in the y direction. On the other hand, speed of the wave, along the string, it is a constant value. C is a constant value. when you talk about the speed of sound in the air, it is a constant value. Speed of sound in air, it is approximately 340 meters per second at room temperature. But when you have the sound wave transmitted in the air, particles move back and forth. So they have positive and negative velocities. And that indicates the difference between the two concepts. One is the energy speed, one is the particle speed. And of course, if the particle have the speed that changes, that also involves acceleration. Typically, once again, that involves differentiation in order to convert the particle displacement into particle speed. But that would be something not we are touching upon in most of the time in this course. Okay, anyway, another way to distinguish, well, whether it is C or whatever, we just give it a particular symbol. We are not strict in terms of the use of symbols, but I'm just trying to use a symbol rather than U to distinguish between two things. Do not associate the concept with one particular symbol. It is just like the case in the kinematics. Sometimes some of the students may use V squared minus U squared equals to 2AS. Some of the students may use VF squared minus VI squared equals to AS. It is the concept that is more important rather than the symbol. So at here, we have another way to distinguish different types of waves, and that is according to the direction of the energy travel in relation to the direction of particle motion. Say in the case of the transverse wave, you have the particles oscillating up and down from their equilibrium position. Equilibrium position is when it is in a straight line. So the particles can move up and down. At the same time, energy would be traveling from left to right. So that is the situation of transverse wave. Longitudinal wave, however, involves the particles motion that is along the same direction as the energy travel. So they are moving in the same direction in the case of the longitudinal wave. Of course, in order to represent the displacement of the particles, you always, in most of the situation, you would use a graph like that. Y versus, for example, X. Y refers to the displacement from the equilibrium position. In both the longitudinal wave and the transverse wave, you would draw something like this, although they, of course, have different meanings. When you draw this graph for the transverse wave, it corresponds to the displacement of the particle from the relative position in a direction perpendicular to the energy travel. When you draw it for a longitudinal wave, it corresponds to displacement of the particle from the equilibrium point along the particle displacement direction, which is the same as the energy travel direction in the case of a longitudinal wave. In both situations, you draw a graph like that, but you should distinguish between two different types of waves. One have the particle moving perpendicular to energy travel. That is the transverse wave. One have the particle moving along the direction of the energy travel. That is the longitudinal wave. So in order to study the waves, of course, we most of the time would represent the particle displacement with respect to x, or particle displacement with respect to time on the graph paper. And simplest types of waves are sinusoidal waves, which are periodic and continuous. So for example, in the graph at here, you have the y versus x, which are sometimes called as snapshots, because you have you are frozen the particle displacement in time. So the brown line corresponds to t equals to 0. The brown line is t equals to 0. The blue line is another time t. And here you will see the wave to be traveling from the left to the right. On those graphs, you will see the wavelength and the amplitude for the case of the snapshot graphs. Whereas in the graphs of the displacement versus time, the separation between two peaks or the separation between two troughs correspond to the period of oscillation. Another way to represent the time of oscillation is the frequency, which tells you how many oscillations can take place at a certain occasion over 1 second. So it is the number of cycles generated within 1 second. And the period t, on the other hand, corresponds to the time required for the particle to complete 1 cycle of oscillation. So period and frequency, they are related by such a relation. And in many cases, the sinusoidal wave could be represented by a general function that looks something like this. It is a sine graph. It is a sinusoidal graph. So you would have a sine function. Of course, different waves have different period, different wavelength, and also different amplitude. So you have to fit in these parameters in the equation. The idea is like this. Amplitude is easy. It comes in front of the sine function. The fitting of the wavelength and the period fits the idea that one oscillation of the sine function, one single oscillation of the sine function, in terms of angle, it is equal to 2 pi radian. So after one oscillation, which in terms of the distance, it is equal to wavelength, it should generate an equivalent angle of 2 pi radian. So that is why you have x over lambda times 2 pi in the bracket. Similarly, over one oscillation at a graph of a y versus t, over one oscillation, it takes the time of one period. So after one period of oscillation, it should be moving over an angle of 2 pi radian. So you have the time divided by the period of oscillation and multiply by 2 pi. So that is why you have the full equation form. A times sine 2 pi times x over lambda minus t over the period t. It can be negative or it can be positive, depending on whether your wave is traveling along the positive x direction or the negative x direction. If it is in the positive x direction, it is a negative sign. If it is in a negative x direction, it is a positive sign. The reason has been explained in the last lesson. And you could always figure it out by trying to draw a series of graphs, y versus x over different time. So t equals to 0, and then t equals to some time later. And you will see that when a wave moves from the left to the right, you would have to fit in a negative sign. So that is the idea. And for some physicists or engineers, instead of writing the equation in a complicated form like this, they would like to simplify the things a little bit, just a little bit, by grouping 2 pi and lambda together. And it becomes what we call the wave number. And they would also group the 2 pi and t together, and it becomes the angular frequency. The name of angular frequency actually hints a connection with the rotational motion or circular motion, but that is not our focus in this course. If you go to the university physics textbook, you will see the connection. I introduced it actually last time as well. So I urge you to go to that section to take a look. And finally, we would have to fit in the situations where the wave may not be starting at 0 when t is 0 and x is 0. Sometimes the wave may be starting something like that, x equal to 0 and t equals to 0. So in that situation, the sine function here within the red square or red rectangle does not fit the actual situation where y has a finite value. So in order to fit in that finite value, we have to adjust the sine function with an additional term. This additional term is called a phase constant. It is a manual adjustment of the sine function so that it could fit in the graph. So it really depends on the actual situation to decide what is the value of phi in your function. So let us try to take a look at an example and see how all the things comes in. Now, you have this sine function or sine wave, and it is a snapshot graph. So y versus x at that, let me see, it has an amplitude of 15 cm, wavelength is 40 cm, and a frequency of 8 hertz. You could see the 15 cm and 40 cm in this graph, but not 8 hertz. 8 hertz is something given to you. Now, the position of an element at t equals to 0 and x equal to 0 is equal to 15 cm. So just like the graph shows, at this graph, t is equal to 0, particle at location x equal to 0 is displaced by 15 cm. So that is basically the maximum displacement in the positive y direction. So now you have to find out what is kt omega and the speed of the wave. To find out the k, you just have to go back to the equation, 2 pi over lambda. And the unit of the k is radian per meter. So it is radian per meter because the 2 pi correspond to an angle in the unit of radian. And lambda is the wavelength, which has a SI unit of meter. So radian per meter is the unit of the wave number. Period of oscillation is just 1 over f. So 0.125 seconds, not much of a difficulty. Angular frequency, omega, 2 pi f. And the unit of the angular frequency is radian per second because it is a multiple of 2 pi, which is an angle with the unit of radian, and f is frequency, which has a unit, well, frequency as a SI unit of hertz, but when you use it as a compound unit, you would put it as 1 over s because f is basically 1 over t. So t is the period and has a unit of seconds. So that is why angular frequency as a unit of radian per second. Finally, the speed of the wave, lambda times f. So you see here in the lecture notes, the speed of the wave, it is written as v. So maybe it's better for me to stick to this v to correspond to the speed of the wave. But hopefully, with the introduction in the question, it may be more clear to you. So speed of wave is lambda times f. And in the part B, you're asked to determine the phase constant, phi, and then write down the general wave function. The equation of the wave function, it is generally written like that: y equals to a sine kx minus omega t plus phi. So when x is equal to 0, when x is equal to 0, t is equal to 0. When x is equal to 0 and t equals to 0, the displacement, vertical displacement is 15 cm. So y equals to 15 cm when t and x are both 0. So you put x 0, t 0, so it becomes a sine phi. And the left-hand side is simply a, if you like, because that is the maximum displacement already. So phi becomes pi over 2 radian because sine phi is equal to 1. So that is why we come up with the equation y equals to a sine kx minus omega t plus lambda over 2, pi over 2, pi over 2. And for those who are good at trigonometry, this actually becomes a cosine kx minus omega t, which does not really surprise you because if you look at the graph, it is basically a cosine function rather than a sine function. So that is how we come up with this equation. Right. So next, we try to introduce some other equations that are relevant to the travel of the waves. In particular, the speed of wave in a string can be determined by the equation shown here. The situation is like this. You have a string that is under a certain tension. For example, you have a pulley and the pulley is holding a mass. So you have some tension in the string. And then the string, of course, is made up of some elements. So there are mass for the elements. And there would be an associated linear density. Linear density for the string, it is equal to the total mass divided by the total length of the string. So it is basically the mass per unit length. And it has the unit of kg per meter. It is not the real density. It is just a linear density. Now, of course, we assume that the string has a uniform distribution of the mass in order to have a fair calculation. So the speed of the wave in this string can be determined by the equation shown at here. Students who play violin or students who have experience with guitar should probably recognize this equation. If not by the formula, you would recognize it by the way in which you adjust the notes in the string. Now, in the violin, for example, at the top of the violin, you have screws. Those screws can be used to tighten the string. The tighter the string, the higher the frequency of sound that can be played. Usually, the wavelength of the sound is determined by the length of the string. Because if you want to generate a particular sound wavelength, you have to adjust the corresponding length of the string. So the wavelength is fixed by the distance between the support of the violin string. And the way to adjust the sound speed is by adjusting the tension in the string. So you tighten the screw, then the tension is increased in the string, and therefore the speed will be increased. So if you have the equation V equals to F lambda, when lambda is fixed, V increase would lead to a frequency increase. That is one way. The other way of adjusting the frequency of the note coming from the string is by choosing the string with different thickness. Some of the strings are thicker than the others. The thicker strings are usually playing lower frequency notes because if the string is thick, then the mass per unit length will be large. when you have a large mu, then the V would be decreased, and this would decrease the frequency of the note if lambda is constant. So that is how we make use of these facts to adjust the frequency of the violin strings. You could adjust the tension, or you could use thinner or thicker strings in order to adjust the speed of sound and therefore the frequency of the sound played by the violin strings. Okay. Right. In order to fortify the knowledge, let us try to take a look at a tutorial question. Let's take a look at question number 6. Okay. At here, you have the scenario, which is basically the same as the one I just introduced. You have a string, and the tension in the string is maintained by means of the mass hanging over a pulley, like the one shown in the diagram. Currently, the observed wave speed is 24 meters per second when the suspended mass is 3 kilograms. So first of all, you're asked what is the mass per unit length of the string. So make use of the equation we have just seen. Okay, now let me see if I could write something. Okay. So in the part A, according to the equation, V is equal to T over mu. So mu is equal to T over V squared. Tension is equal to rate, mg. So the mass is 3 kilograms. In the answer of the tutorial question, it uses 9.8 instead of 9.81, but the difference should be very small. So let us stick to the tutorial answer and use 9.8. 24 squared. So in this way, you would get the answer of 0.051 kilogram per meter as the answer. And then you change the mass to 2 kilograms in the part B. When the mass is changed to 2 kilograms for the same string you could write something like this: T1 over V1 square is equal to T2 over V2 square, because mu is constant. So putting T1 equals to 3G, T2 equals to 2G, well, 2 times G, not 2 grams, 2 kilograms times G, and V1 equals to 24 meter per second, and then you would get what is V2. So that should be 19.6 meter per second. That is by the comparison of the ratios, okay? In tutorial 4, question 5, you would be asked to calculate what is the angular frequency, that is omega, and the wave number, k, which is 2 pi over lambda. Omega is 2 pi f. And you are asked also to write an expression for the wave function. So expression is y equals to a sine kx minus omega t plus phi in general. So you just have to put in the various numbers to find out the expression. The parts D and E, I think you may not solve without understanding the operation of the differentiation, because the transverse speed it is equal to dy over dt. That is rate of change of the displacement. And if you see that it is a differentiation of the sine function, if you have not learned it, you do not know it, basically. So if you have not learned it, there's no need for you to try to attempt it, because that would not be tested, to put it simply. If it requires the actual differentiation, either you are given the equation, or we would not ask it simply in the midterm or examination. If it is to be asked, you will be given corresponding support for the differentiation part at least. So similarly for the part E, transverse acceleration, it is equal to second order derivative of the y with respect to t. So once again, that is not to be asked unless equations are given to you. Okay, the students are asking why t over v squared is equal to m over l. That is related to the equation we just introduced in the lecture notes. Remember, before we come to this tutorial worksheet, we were talking about this equation. So What does that mean? Mu is equal to T over V squared. For the same string, mu has not changed. Therefore, for the same string, if tension has changed, V has to be changed. So we could write T1 over V1 squared. For situation 1, that is equal to T2 over V2 squared for situation 2. Situation 1 is when the tension in a string corresponds to a support of 3 kilogram mass. Situation 2 is for the support of a 2 kilogram mass for the string. And okay, so hopefully you got it. Yes, second order derivative of y with respect to t sometimes is written as y double dash. But of course, that is for those who have learned differentiation. If you look at the diagram, it is a displacement in the vertical direction. You are shaking the string up and down. So the particles are displaced up and down. The energy, on the other hand, travels from left to right. That is the transverse wave. Yes, the equation is for sinusoidal waves. If you have other types of periodic waves, you have to first consider them to be a sum of various sinusoidal waves. So at here, we just learned the concepts by looking at the simplest type of wave, which is the sinusoidal wave. Right. Now, just before the break, let us take a look at the final topic in chapter 16. And that is concerned with the reflection of the wave when you are having the end that is fixed or that is free to move. So the idea is basically the one borrowing from the Newton's third law. When you have the particles in the wave that is displaced, for example, in the upward direction. So here you see waves are displaced upward. The particles are displaced upward while it travels from left to right. Then when the particles are hitting, well, when the wave is hitting the fixed wall, of course, the fixed wall would suffer an upward force because the particles are being brought upward. So there must be an upward force that brings them upward. This upward force would be transferred to the wall. At a revenge, if you like, as a revenge, the particle, by the Newton's third law, would provide a downward force to the particles in the string. So that is why when the wave is reflected at a fixed end, particles would be brought downward when they are reflected. So when the wave is reflected, the downward force is provided by the wall. Yes, because of the Newton's third law. You have the particles in the string that tries to bring the wall upward. Of course, you cannot see it because the wall is much more massive compared with the string. And at the same time, the wall would provide a reaction force that brings the particles in the string downward. So when the wave is reflected, particles are displaced downward. That is the natural consequence of the Newton's third law. On the other hand, if your string is connected to a free end, for example, like the one shown in the diagram, it is connected to a ring, supposed to be free of any force. When you move the string particles upward and the wave travels from left to right, when it hits the end, it brings the whole thing upward. So the wave would just be reflected with the particles still displaced in the upward direction. The ring does not provide any reaction force to bring the particles downward. I'm not quite sure what that means. If the string is continually moved up and down, why don't we see the reflection? We see the reflection. We are seeing the reflection. The wave is reflected. It is just that it is reflected for once. Well, you have one pulse, then you reflect it once. The ring, if it is on a smooth pole, it just is brought to motion by the upward force of the string. So it does not provide any reaction force. That is, of course, provided that your pole and the ring is smooth. So that is when you have a ring that is connected to the string and it is on a smooth pole, no vertical force could be provided to the string, unlike the case of the wall. So that is the two different situations when the wave is hitting a fixed end and a free end. And this concept actually becomes useful even in a case when you do not have the material wave. For example, the light wave, you would have the similar issue. But of course, the situation would be slightly different because you do not really have fixed particles or free particles. But when you have the light being reflected from a high refractive index medium, then you would have the phase change. And that is something we would introduce only in the physics 2. So at here, we just have a very quick introduction of the concept of wave reflected at the fixed end and the free end. So that is the idea. Okay, now I will take a break about 10 minutes. And then afterwards, we will be moving to the next topic of the oscillatory motion. So coming back a little bit to the mechanics, although they are certainly related to the wave motion as well. So I would come back at 10 minutes time. right? Okay, now we will return to the lesson, and here we would be actually stepping a little bit backward and talk about the motion of the particles, if you like, in an oscillating system. So you could easily associate this type of motion to, for example, the particles moving in a medium of a wave. For example, the water waves or the particles in the string wave. If you have a continuous wave, the particles are moving continuously up and down. So the motion of the particle as a function of time, would be concerned with this type of oscillatory motion. So that is the focus of the this chapter 15. And in particular, we will be looking at the motion that we call the simple harmonic motion. It is the basically simplest type of motion, and the description of such a motion can be considered by checking what causes the oscillation motion. So we have two systems in particular that we would consider having a simple harmonic motion. One is a pendulum with a spring connected to a mass, and the other one would be a pendulum that contains a heavy mass connected to a string. So the second one is something we typically call the simple pendulum. You could easily find a simple pendulum when you Google and find lots of old clocks. Those are large clocks standing on the ground, and they have a very large, very heavy mass stuck at the end of a rod. So they keep on oscillating, and those are something like a simple pendulum. And so at here, let us try to take a look at what we mean by the simple harmonic motion, or in general, the motion that are periodic. Basically, it refers to the type of motion that would return to the given position after a fixed time interval. So it refers to a situation when you have the particles from time to time, either X or Y, let us call it X. From time to time, it would be coming back to the same location after a fixed time interval. So this fixed time interval is usually the period of the oscillation. So that is the period. We do not concern too much about the wavelength here because we are taking a look at a particular particle in the oscillatory motion. So how the wave transmits is no longer a concern here. We are just looking at a certain particle, how it moves from the equilibrium position from time to time. So that is why from this point onward, we would be mainly drawing this type of graph, X versus T, as a function of time, how the particle displaces from the equilibrium location. So this periodic motion must be returning to the given position, and it would happen over fixed time intervals. That is why it is periodic, because after certain time, it will come back and keeps going forever and ever. So that is why it is periodic. And in particular, there is one type of a periodic motion that would be very important, and they are called a simple harmonic motion. Now, for this type of a simple harmonic motion, it has a functional form. It has a functional form that is very, very, very similar to our wave equation that I've just seen. Although we have to be very careful that here, once again, we just look at one particle, how it moves as a function of time. One particle, how it moves as a function of time. So we are analyzing only one single particle on the oscillatory motion. And in this type of a motion, the particle displacement as a function of time, actually, as we will see later, it is sinusoidal. So it would be having a sine function once again. But what is more interesting here is how this type of a periodic motion can be present. So that would be the important topic of investigation at here. The simplest or the easiest to understand periodic motion can be observed when you have a mass connected to a spring. Say we have this setup put on a smooth table, assuming that no frictional force, no other forces that are present. At the equilibrium, when you place the particle on the table, and if the spring is not extended or compressed, there is no force acting on the particle by the spring. Everything is not moving. Everybody stands still. That is an equilibrium situation. So there is an equilibrium point, x equals to 0, when there would not be any force acting on the particle by the spring. Once again, no frictional force. So it has to be a frictionless horizontal surface. Now, think about what happens when you extend the spring, and this spring is connected to the particle. When you extend the spring, of course, there is a force associated with the spring. This spring force would be trying to bring the particle back to the equilibrium position. Now, things are still quite straightforward so far. When you use your hand, for example, to pull the spring from the equilibrium point, or pull the particle from the equilibrium point to the position X, of course, you have to provide a force. That force would be equal to the tension in the spring, if you like. The spring itself would be providing a tension. The spring tension is in the direction opposite to the particle displacement. Now, that is a very important message. The spring force would be in the direction opposite to the particle displacement. Now, let us release the system. When you release the system, of course, the spring has the tension Fs. Remember what's the direction? It is pointing towards the equilibrium position, x equals to 0. So what would happen? Of course, the particle would accelerate it would accelerate back towards the equilibrium position. As it moves closer and closer to the equilibrium position, the extension of the spring gets smaller and smaller. When the extension gets smaller, according to the Hooke's law, the force coming from the spring should be smaller and smaller. So this would carry on until the particle comes back to the equilibrium point. When the particle comes back to the equilibrium point, what is the spring force? The spring force would be 0. So no acceleration on the particle now. But wait, when the particle is released, it has 0 velocity. When the particle comes back to the equilibrium point, would it be at a 0 velocity? Of course not, because it has been accelerated by the varying force of the spring. Although the force is large at the beginning, it becomes 0 when the spring or particle comes back to the equilibrium point. But the particle has a velocity. And very, very importantly, particle has inertia. It has a mass, so there is an inertia. What happens? Due to the inertia, the particle keeps moving. When it goes past x equal to 0, it keeps moving to the negative x direction. So when it keeps moving, what would happen? The spring becomes compressed. Then there would be a force from the spring to the particle. And this time the force is pointing towards the positive x direction when the particle displacement is in the negative x direction. Once again, force is opposite to the particle displacement. Once again, force is opposite to particle displacement. So what happens next? You would guess, eventually the particle is decelerated and it would come to a stop. Well, you do not need mathematics, you do not need physics, you need common sense to understand this. The particle would be brought to a stop because the spring gets a stronger and stronger force to decelerate the particle. So eventually it stops. When it stops, the spring would provide the force to push it back to the equilibrium position. The story repeats, but in the opposite direction. So we can kind of understand what is happening, at least in terms of the particle motion and the spring force. Let us try to repeat it. At the beginning, the particle is displaced. The particle is displaced from the equilibrium position of the spring. So there is a force from the spring to pull the particle backward. It keeps on pulling it, but at the same time, the force gets smaller and smaller. So it comes back to the equilibrium point. The particle comes back to the equilibrium point where the force becomes 0. At that time, the particle has velocity, and because of inertia, the particle overshoots the equilibrium point, and it keeps moving to the negative x direction. So the spring is compressed. It provides a force that opposes the motion. So when the particle is finally stopped due to the deceleration of the spring, deceleration forced by the spring, the particle would come to a stop and it would be pushed back to the equilibrium point. and the motion repeats. So it is a never-ending story, apparently. But there are two important components. Let us not look at the mathematics first. Let us just look at the physics first. There are two important components at here. First, you need a spring, or actually, you need a restoring force. Why is a restoring force important? The force has to be present in order to bring it back to the equilibrium point. And that is why it is restoring. It brings it back to the equilibrium point. It always do so. It does not bring it to the positive x when it is displayed from the x equals to 0. Otherwise, it goes to infinity and disappears. It always tries to bring it back to the equilibrium point. So this is a restoring force. That is the first important ingredient for any oscillation motion. Secondly, there is inertia. If you do not have inertia, what would happen? The particle stops right at the equilibrium point. But because of inertia, it keeps moving. It overshoots the equilibrium point. And that is the how the story goes on without any stop. You have a restoring force that brings it back to equilibrium point. And because of the inertia, it does not want to stop at equilibrium point. So the story keeps on going forever and ever. And that is the oscillation motion. Now, mathematics. We could set up the motion in a very simple way. The first equation, at least, is simple. We can use the Newton's second law to describe the whole thing. I am saying that the first equation is simple. I do not say the second equation is simple. The first equation says you have the force. This force provided by the spring points in a negative x direction. And it is equal to mass times the acceleration. At any point, this is always true. There must be a spring force, which is given by minus kx. And that is, according to the Newton's second law, equals to mass times acceleration. So we have the first equation, ma equals to minus kx. This equation includes the two ingredients we just talked about. First, restoring force. It is a force because from the kx. It is restoring because of the negative sign. It points to the equilibrium point. It is restoring, not reaction force. It brings it back to the equilibrium point. It is restoring, not reaction force. And finally, it has inertia because of the mass. So the simplicity ends here. And then it is a hard part. According to the integration or differentiation or calculus, whatever you call it, acceleration can be written as second order derivative of x with respect to time. So we rewrite the equation like this. M times dx squared over d squared x over dt squared equals to minus kx. And then we could rewrite d squared x over dt squared equals to minus k over m times x. So the important point is the acceleration, it is proportional to minus x. acceleration is proportional to minus x. And this is the defining character of simple harmonic motion. If you find that for a motion, the acceleration is proportional to x and it is pointing in the opposite sense as the x, then you could say it is going to perform a simple harmonic motion. That is always true for simple harmonic motion. The proportionality constant varies, and in general, the proportionality constant is written as omega squared for some very special reason, as we will see a little bit later. So for the time being, let us say the acceleration is equal to minus omega x squared. And to solve this equation, to solve all these equations, it is certainly at the level of calculus lesson. So we are not going to really solve it, but we try to suggest a solution as you would imagine. The solution would be a sine or cosine function. Let us say it is a cosine function. So the position of the particle as a function of time, the position of particle as a function of time, that is what makes up the left-hand side of the equation, x as a function of t. It is equal to a times cosine omega t plus phi. A refers to the amplitude of the oscillation motion. If you draw this graph, x as a function of time, well, let's try to do it like that. A corresponds to the amplitude of your oscillation motion. That is the maximum or the minus maximum, if you like, of your graph. Phi would be used to adjust the starting point of t equals to 0. We will talk about it a little bit later. Omega, on the other hand, would be similar to the wave function or wave formula that we have seen in chapter 16. It is related to the period of the oscillation. If you do not believe me that it is a solution, you have to first learn differentiation. Once you learn the differentiation, you could differentiate x with respect to time twice in order to get the acceleration. And you would find that a is actually equals to minus omega squared x. So this equation truly is a solution. This equation at here is a solution to the equation a equals to minus omega squared x, where in this particular situation, omega squared is equal to k over m. And it is omega squared, so it is a positive number. K is a spring constant, it is a positive number. Mass is a positive number, so it is by itself is a positive value. Omega is square root k over m. So for this cosine function, the period of the oscillation can be obtained by the relation 2 pi over t. as we have seen in the wave formula in chapter 16. So here we have very quickly introduced the equation of motion for the simple harmonic motion. The equation of motion basically always have the form A equals to minus omega square x. Omega square varies from situation to situation, but the acceleration is always proportional to x with a negative sign. That is the characteristic of the simple harmonic motion. Omega contains the information about the period of the oscillation because omega would be equal to 2 pi over t, just like the case of the wave equation. Okay. And in the previous general solution, we have the phase angle phi that comes into the formula, that comes into the solution. What is its use? Well, the use is that you might have the situations changing from one into another. And here are two particular cases where we will show you phi is useful. The phase angle is useful to adjust the situation. Let us consider the same problem. The spring connected to a particle, but with different starting situation. So the first starting situation refers to this. X at time equals to 0 is A, and V equals to 0 at time is 0. Now, what does that actually mean? Basically, it refers to the particle. It refers to a particle that is held at a distance A from the equilibrium point and keep stationary at the beginning. So when time is 0, the particle is at the location x equal to A. And because it is held stationary, V is equal to 0. That is the situation. Now, with that, we could put it into the general solution form, xt equals to A cosine omega t plus phi. When t is 0, x is equal to A. So t is 0, omega t becomes 0. And A cosine phi is equal to A means that cosine phi is equal to 1. Phi has to be equal to 0. So that is why phi is 0. And therefore, the whole solution for x becomes A cosine omega t. What about velocity? For the velocity, let us refer to the previous page. Velocity is minus omega A sine omega t plus phi. So we just put the things back into the equation. Phi becomes 0. So it becomes minus omega A sine omega t. Acceleration minus omega square A cosine omega t. These two comes from the previous page. These two comes from the previous page. When phi is equal to 0. So how do we understand the answers at here? We try to draw them on the graphs. The first one corresponds to x versus t. This is first one, this is the second one, and this is the third one. First one corresponds to x versus t. Second one, velocity versus t. Finally, acceleration versus t. Notice a few things. First, amplitude of all these graphs. For the first graph, the amplitude is A. Second one, the amplitude becomes omega A. Finally, the third one, acceleration is omega square A. So the amplitudes of the displacement, velocity, and acceleration, they are somehow related by omega. That is the first observation. Secondly, what is the period of the oscillation? It remains unchanged. It is always t. It is always t. So from all this graph, the oscillation period is always t. So all the things would repeat itself after a time t. And finally, the particle displacement, velocity, and acceleration, they are not moving up and down all in the same pace. But you could see that when one is a cosine graph, say the first one is a cosine graph, the velocity is a inverse sine graph. And then the acceleration becomes an inverse cosine graph. Mathematically, they are related by the phase difference. There is a phase difference between the graphs, but let us try not to make the things more complicated by now. In any case, they are not moving up and down at the same time. So they would be having different starting values, if you like. So that is the case of the spring initially pulled to x equals to a, and then released from rest. And that is example number one. Of course, the particle can be set into motion by other methods. And that would be case number two. In the case number two, we have originally the particle staying at x equal to 0. So no extension of the spring at the beginning. And then all of a sudden, we give it a kick. So it has an initial velocity v when time, well, vi maybe, when time is equal to 0. And x is equal to 0 when the time is 0. So that is the initial conditions as highlighted here. T equals to 0, x is 0, and v is equal to vi. Now, with that, we would have to be careful. X is a cosine omega t plus phi. But at t equals to 0, x is 0. So a is not 0, of course. Cosine omega t, which is 0, cosine phi is equal to 0 because at time equals to 0, x is 0. So cosine phi is 0, phi becomes pi over 2. or actually it can also be minus pi over 2, because cosine phi can be 0 when it happens in two situations. So we have to go to the second condition. When we consider the velocity, if you go back to the equation at here, it is Vt equals to minus omega A sine omega t plus phi. So let us copy it to this page. Vt is equal to minus omega A sine omega t plus phi. So when t is 0, minus omega A sine phi, it is equal to Vi. So if Vi is a positive value, then sine phi has to be negative, say negative minus 1. And therefore, phi has to be a negative value. And that is why it comes to phi equals to minus pi over 2 instead of plus pi over 2. Because the velocity starts from a positive value. So phi is a minus pi over 2. So the equation here has replaced phi by minus pi over 2. So it is becoming A sine omega t. For the velocity, it is omega A cosine omega t, and acceleration minus omega square A sine omega t, because we have put phi equals to minus pi over 2. Once again, if you try to put plus pi over 2, the equation at here does not add up, because Vi is moving in a positive direction. Vi is positive. So we are setting it up to have a positive value. So therefore, the left-hand side must be positive, meaning that sine phi must be negative. And so phi has to be negative. So that is the idea for the second example. So the exact equation has to be determined based on the exact situation. So you always have the general solution, which is the one at here. The general solution is x as a function of time equals to A cosine omega t plus phi. The value of phi has to be determined by the initial conditions. So sometimes you can use the initial displacement to determine the value of phi. Sometimes you have to use the initial velocity to determine the value of phi. That is the situation for example 1 and example 2. Okay. Now, just to briefly recap the period of the oscillation. As I've said, it is related to the omega. So omega is equal to 2 pi over t, and the time t refers to the time interval required for the particle to complete one oscillation. It is the time required for the particle to complete one oscillation. And so we could try to understand it like that. After one oscillation, all the things would be repeating itself. So xt plus the period would be equal to xt itself, simply because the oscillation pattern repeats after one period of oscillation. Of course, when we write xt plus t, we are referring to, well, assuming phi is zero, we are referring to a cosine omega t plus large T. And one period of oscillation should build in a phase angle of 2 pi, because over a 2 pi, you would have repeated the oscillation. So the phase angle involved would be equal to 2 pi. So omega t here could be written as 2 pi. And when you have the term at here, and it is in a cosine function, it is actually equal to cosine omega t. So that is why the 2 pi can be removed and becomes the equation at the next line. So in any case, omega t is equal to 2 pi, and therefore omega is equal to 2 pi over t. So the omega is the angular frequency. It is related to the frequency of the oscillation by the equation omega equals to 2 pi f. Right. I probably would stop at here for the time being. Okay. Why 2 pi can be eliminated? Well, think about what is cosine theta plus 2 pi. Cosine theta plus 2 pi, what would it be? It is equal to cosine theta. Okay, now give me some time to talk about the midterm. I'm not talking about the results. I'm not talking about your performance. In any case, you should be able to see the performance by checking the marks yourself. But just one thing you may notice, and that is the question number 9. If you check the marks, some of you may be puzzled that you suddenly have 3 marks increased from the original marks. The reason is because when we set the question, we have overlooked the issue of parameters. Basically, when we set the questions, let me see. Basically, when we set the questions, we let the computer to play around with some parameters. And that happens to be a bad choice. Well, we have to use the computer to generate some random numbers so that it allows different students to have different answers, but sometimes the parameters would give you physically meaningless combinations, and that is something we cannot check until students tell us. For example, in the question 9, it happens that accelerations becomes larger than the acceleration due to gravity. So the calculated moment of inertia becomes negative, which is physically meaningless. Some of the students have the difficulty to work out the answer in a certain combinations of the parameters. And after discussion, we think that we may just let all the students get the full marks for this question. So basically all the students would be scoring the same mark for this question, irrespective of their final answers. And for the rest of the questions, there would not be any change. So that would be the situation, okay? Now, I would not, as I've said, explain the answers one by one. If you have questions, please ask me during the consultation hours. Please check the question. If you have initially answered it correctly, there would not be any increase of the marks. You only have the mark increased either if you have not answered it or you are not able to answer it. So it is not the most perfect arrangement. In the most perfect arrangement, we have set the question correct. But rather than deleting the question altogether, which would bring difficulty to the students who answered correctly and actually got the marks deducted, it is actually bring all the people happy by giving marks to all of you for that particular question, okay? So we try to treat it in this way. I would handle your situation separately, okay? Please stay after the class and we would handle it. Right, I would stop the lesson at here and we would carry on with the lesson next Tuesday. But before we leave, I'm always happy to leave you some exercise to work on. So in-class quiz is already available. There is one single question and you have to do it within today. Please submit it by the end of today. The computer treats the end of the day as 11:59. It is 11:59:00, not 11:59:59. So do not play with that 1 minute. It is set at 11:59:00. So you better do it before the due date, okay? Next Monday is a holiday, yes. So we would not be having the lesson. Well, depending on the how hectic the schedule would be, we would skip that lesson and we would continue in that case next Thursday. Okay, I will stop the lesson at here. Thank you.